Okay, so today's lecture will be about dynamic experiments. And that's a type of experiment that produces a lot of data. And there are some things you have to think about when you start doing these and also for the analysis afterwards. So first, a little bit literature. As usually, we have John Ross, which is always a good place to go back and get some ideas. Another one is a book by Gostabig, which is about image registration. And that's something I will talk about later, but an important topic for dynamic experiments. Then there are some papers and links that you can take a look at. Let's go through essentially what we are going to talk about in the lecture today. We have already talked about many things. We are going towards the end of these lectures, and we started out with some basics about images. Then we talked about enhancement to get rid of noise. Noise is actually a thing that is very prominent when you talk about dynamic experiments, because what you usually want to do is to push the system to the limits of what it can in terms of spatial and temporal resolution. And the cost is that the images get noisier than you normally would like to have them. Then we looked at the histograms, different automatic methods for segmentation, and also important is the labeling to identify different pieces. And then analyze these shapes in different ways. So the topic is about big imaging, and now it's not only about it's big or large, but it also means that we should be able to handle this data. It's not only producing 10 hard drives full of data, but actually to be able to cope with it and get some real information from it. And an important thing is that we have three V's: the volume, how much, and how big each is. Then we have the velocity. So when we do dynamic experiments, something is moving on. And another thing is, usually we want statistics, so we also need some degree of variety in the data. Of course, when we do, to be prepared for this, we need to be scalable, we need to be fast, and we also need to be able to easily customize the code for maybe a little bit different conditions between experiments you do. Not to rewrite the code every time you do a new experiment. So what we need to do, we need to do the analysis in very disciplined manners. We have the fixed steps. First we filter, then we segment, then we label, etc., etc. And it should be easy to regenerate the results. So if you realize, filtering this way wasn't good, so we need to redo the filtering. And if we do that, we have to do the whole chain again. And that shouldn't be done using a lot of different clickings and hand wavings, etc. So there shouldn't be any magic in this processing. And it shouldn't be bound to a single person who does it, because if that is the requirement, then you would have different results depending on who is working with the data. So you may have acquired data and done the first analysis, but some poor master student or PhD student coming after you also needs to use your data to complete their data set. And then there shouldn't be too much magic or too much strange things on the way for them to take up the data again. And of course, automating the process is also very important, because in particular, based on today's lecture, we will maybe have 100 samples and those over time, and that is a lot of data to process. And you can't sit at a computer doing hundreds or thousands of images and do that the same way. So you need to really have a reliable automated processing. And of course, ability to adapt and reuse the analysis is always good, because what you once written is written, and if you have to redo that all the time, it takes you maybe one day extra every time. But if you can reuse the data, your code, then it's maybe possible to get up and running within 2 hours instead of a day, or even more, depending on what you are doing. So it should be easy to script, making everything scriptable. I touched that a little bit last week, but we should also be able to handle different kinds of cells or different kinds of regions, etc., etc. So imaging of dynamic experiments. So first, I would like to make some definitions here. And first, what is a dynamic process? So it's very abstractly something that relates to objects in motion. So something is not, so until now we have been talking about things that are always in steady state. They are standing nice and still, but that don't do much more. Then the other thing is it's also characterized by some kind of continuous change and activity or progress throughout the experiment. For dynamic experiments, it's often talked about real time. So that is, it has many definitions, real time, but it's essentially the time you acquire while things are going on, and you should be able to capture it. And in computing, there is always the talk about real-time systems, and this is in principle that the data should be available so that you have a virtually immediate feedback from the processing. Real-time, in this case, when we're talking about experiments, is mainly about how well you can capture the process. I'm not talking about doing the analysis in real time. So meaning in one moment you acquire the image and next moment you have the result. That would be nice, but it's mostly not realistic. You can have some simplified real-time feedback or quasi real-time feedback, but usually the analysis is something you do offline after the experiment. And of course, we have the imaging part here that you should be able to capture, store, and manipulate and display the data that comes in. In particular for real-time experiments, it's the frame rate and storage capacity, which is important to think about. You should be able to acquire the data at the rate you need it for to be able to study your process. And of course, it's not only about capturing, because that's the easy part. Well, that's one part of it, capture display. But the other one is being able to store the data as well during the experiment. So you need to have fast hard drives or hard drive stacks, depending on the type of experiments. Like multi-channel parallel drive systems, etc., may be needed to be able to keep up with the rate that the detectors produce the data. Then we have different types of experiments. We have, and depending on which kind of experiment or process you want to study, you have different approaches how to measure. So if you have a continuous process, which is, I would say, in very many cases, then you just press the button, start something, or you inject some something new into the system or give it some kind of input that kicks on the process. And then you observe what's happening with the acquisition. The other one is repetitive. So that is something that goes cyclic. You can, well, here I have a picture of children on a swing. They go back and forth all the time. But another one would be if you study, for example, an engine which is rotating, and you can see how the pistons are going up and down. That's also a repetitive movement, and very fast one. And thanks to that, we can actually use trigger signals to identify where the cycle starts. And then we acquire and accumulate for every repetition. And then we can sum up the results. And with that, we can also increase our intensity statistics, or the count of charges in the images. So the image analysis, how to go along with that. So first is the question how we can track objects between points in time. Can we also track the shape or track distribution of objects? How can we track topology, or actually tracking single voxels? Is it possible to assess deformation and strain within the data? And how can we assess even more general cases? So there are lots of questions you have to go into asking. I'm not going to talk about all of these today, but like distribution tracking or shape tracking, I'm mainly going to focus on the things about tracking objects and also making sure that we have the images aligned in the right way. Well, we have different kinds of experiments, and also I'm going to show that a little bit now. So we have different ways to look at how to track changes in the image. So we have pixel and voxel based methods, which works with some kind of correlation. So you can use cross correlation between the frames. So you can use digital image correlation, or which is also called DIC, or DIC plus physics. So then you also include a physical model within in this tracking. You can also look at affine transformation or non-rigid transformations between from frame to frame. So these all look into how the pixels are changing, but you also can look at going one abstraction level higher and looking at key points, so identifying characteristic points throughout the image and use those for your tracking. And then we can look at different thickness and also different problems that you can look at, like thickness of lung tissue, or the curvature of some metal system, 2-point correlations in volcanic rock, so on. So there are a lot of different problems that can come up with this time analysis. And here we already know that analyzing in 3D is already difficult. You can't easily get the 3-dimensional information on a 2D screen. So you can do a lot of volume rendering and stuff, but still doing the analysis, you have to add a little bit more thinking when you do it in 3D, because it's not so easy to see what's happening on the different planes in the image. Taking that one step further, then we go into 3D movies, which is what you have here. Some foam bubbling up, and you can see how this foam is doing something. This is only, I think, 3 frames, so it's not so much going on here. But anyway, that is actually a 4-dimensional data set. So we have the X, Y, and Z, and we have the time axis as well. That's doing analysis in 4D, you usually have to make some kind of reduction before you go into the 4th dimension. For example, filtering in 4D is quite a tricky task to get right. Okay, convolution would be easy, but there are higher dimensional filters, and understanding or getting into your head the fourth dimension is not trivial. And bringing that over in code is even more challenging task. This is something that is not so much available in commercial code, to my knowledge. Well, there is always some little feature of it, but not in too large degree. Then we have also actually 2D movies. So then they are actually 3-dimensional because you have X, Y, and T. And here is some experiment with a fast water jet going through a tube, and you can see the bubbles in it. Yeah, so it's a very fast process going on here. And here we see also that it's very noisy. And another one would be a movie that I made as a demonstration example, putting a kettle of coffee and let it boil. And then you can see over time how it evolves, and how the water is boiling off, and the vapor goes through and form water again, and the water is building up within as coffee. This is a movie I uploaded on YouTube. So if you like to watch how coffee is made within this mocha, then you can take a look there. Again, as usually, when you start doing analysis, you have to ask yourself which information you're looking for. And it can be, so it must be something that you can quantify. And first question is, how fast is something going? How many particles are present? Are the sizes constant? Are some moving faster? Would that be related to the size? Are they rearranging? Are they clustering? And so on. So questions like that, we can actually answer with the help of what we have learned until now. But now we add also the time to this analysis, so we can see how things are moving over time. 3D reconstruction is something that we do a lot in imaging, and as also in hospitals. This is the extension of the normal 2D radiography, because it's rotating the sample, acquiring projections in many directions. And then you can see like this, we have a patient where the gantry is rotating and producing these images. This will give us a 3-dimensional information. But also here, we have to be very careful, because no patient is lying perfectly still, unless they are really constrained by frames or something. That also exists, but in particular, if you look at a tomography of the chest region, it is not easy to get all the different motions under control. So for example, you can control your breath, but you can't control the heartbeat, not very much at least. Also, there are, in the lower part of the abdomen, there are also a lot of organs that are moving around, and that's something you also can't really control, how they move. So there are many frequencies of motions within the body. And for tomography, the requirement is that the specimen or patient has to be still. Otherwise, you will get motion artifacts. And that's a tricky challenge, actually, in medical imaging to handle. Another thing is producing microscope images with stage tilting. It's also producing 3-dimensional images to give you some 3-dimensional depth. Also, that can be used in time series analysis, and then we can look on to that. So what are the goals of a dynamic experiment? One is rheology, to understand how different fluids move around or mix in in a specimen or in a process reactor or something. Another one is looking at deformations, so looking how things are changing shape over time. And here we can see two different medical applications, and also one in, I would say it's probably civil engineering. How you, if you compress wood, what happens and how get it tough. Through that, there are some manufacturing processes doing this. Up on the rheology, it's also again about movement of the blood, but it could also be in porous media. That is a very relevant task, to look how fluids are moving around in rock, soil, construction materials, etc. Also bubble formation. Here is airflow through a dough when we are baking bread, or magma gas formation in a volcano. So these are experiments that actually have taken place and produced this kind of data. When you do dynamic experiments, there are a lot of things you have to prepare first and plan already when you do the experiment. So you may have limited field of view. The voxel size will limit you. I will come to that a little bit later also. Also, the maximum rate of the measurements is something you have to maybe adjust. There is a limitation of what your system can acquire. Does that match what the process is actually requiring? Then there are dose limitations. One on the upper limit is sample damage, that the sample gets damaged by the radiation. The other one is limited flux, that you're going so fast that you don't have enough photons to acquire to follow the process. And of course, there's always some cost for each experiment, so you can't do too long experiments or too complicated experiments. So you have to adapt for that. And usually you have to balance between looking at high spatial resolution and high temporal resolution. Sometimes you can do both and get a good result, but mostly you have to choose one that is more relevant than the other. And the factors that affect the image quality is, first of all, the process speed, but also the spatial resolution and intensity dynamics. So if looking at the speed, you can see in this picture, oh, sorry, I have to close that one. Stop. So, sorry, that was a phone coming in. Looking at this little river, you can see in this part, the water flow is pretty slow, easy to resolve things under it. But then when it goes over the edge, it starts falling faster. And then you can see there is a lot of motion blur. So in this case, we couldn't capture the full detail of what's going on. And that's something we have to balance. In some cases, you can just say, it's fine. Sorry again. Jag kan en voorlezen. Let's look at an example. So we have a dose-limited experiment. And we start out with 100 micron pixels, 1 second exposure time. And as I'm working with neutrons, I'm saying we have 800 neutrons available per pixel as it is right now. And if you want to change something of these, you can't change the number of neutrons because that's given by the source, but you want to increase the frame rate, then you have to make a shorter exposure time. But to maintain the signal to noise ratio under those conditions, you have to make larger pixels. The other way around, if you want higher resolution, then you also have to go for longer exposure times to get the same signal to noise ratio. And actually, this one, the pixel size goes quadratic, so it's really expensive to increase the resolution, spatial resolution. One trick you can do, looking at the scale, is so if you increase the pixel size, and you can see you can't resolve fine features, but you have better signal to noise ratio. Just to compare between these two, you can see that I think I did something like 16 by 16 large pixels. So one pixel is made out of 16 by 16 pixels. And you can see, okay, you can see the core structures. In some cases, this may be sufficient for your analysis. Then it's fine. And then you can go on even faster. But if you need the small details, like the cracks around here, they would be lost. So you have to be careful on this. When it comes to refrain rates, you have to sample in a way that you have sufficient many points throughout the race of some kind of transient change in the process. So in this case, I have pretty many. I would say you need something like 5 till 10 steps on a step to really follow it well and make a good prediction from it. So this would be the opposite, where you just have one point where the rise starts and one point when it's ended. Then you can't even see what's going on in here. An option which has been used in cases when people can't get the frame rates needed is to work with piecewise constant. So then you do, if you can control your process, then you can say you go to one level where it is stabilized into a steady state, do your measurement as long as it's needed, and then you ramp up going to the next level, and you continue like this until you have some kind of ramp or step behavior that you can follow. So it a little bit depends on how much you can control the process, and if you're going for the just continuous sampling or piecewise constant approach. So when you plan the dynamic experiments, a little bit of a summary here. You have different feature sizes versus resolution. So here you would go towards smaller pixels. You can have, would maybe need increased frame rate, or sometimes the image is too noisy, and then you have to optimize for that. And then that usually means you have to have larger pixels and or different slower frame rate. So all these together, you have to balance. So if you're too slow, you would miss small features and rapid changes, and also get some motion artifacts. If we are too fast, we may damage the sample. Can also miss some effects of long-term changes. We get noisy data. The thing with sample damage is that, for example, if you do a tomography, maybe it's actually process damage, but if you do a tomography, and normally that's relatively slow, but if you speed it up, for example, the Tomcat, they do, I think it's 100 Hertz tomographies, then you have to really think about the G-forces, because under some conditions, you really get up to 40 G. And if you have a fluid, a liquid in a porous medium, then it will just splash out along the walls. So you have to be careful about balancing these centrifugal forces against the gravitational forces and the capillary forces. So that's a tough balance to also plan. To high resolution is, well, usually the cost of too high resolution is that your field of view is becoming very small. So you may not be able to see the whole sample. And to low resolution, the cost of that is that we may not see what we want to see. So there are a lot of things you have to balance together in order to get the right balance of acquisition parameters in order to get your data in the right way. If you have a simple process looking at a movie, you can actually extract frames. So the movie you can see as a three-dimensional image. And two directions are the X and Y coordinates, as you normally see them in the movie. And the third dimension is the time. And from that, you can extract a time-space image. So in this case, I'm looking at something that's bouncing up and down. In the movie, you can just see that it's going up and down. But if you extract a frame just in the place where it's bouncing, you can really get a nice image that follows the motion. And then you can analyze the motion through this image instead, which makes it much easier. And also, some cases, easier to visualize what's actually going on. And here is an example that I usually do as a student exercise at my beamline. This is done with using neutron imaging, and neutrons, they are very sensitive to hydrogen. So we see the rise of water very well. It's just like day and night difference, as you can see in this image here. And the experiment is going on like this. It's not very exciting to look at, but anyway, it's a front that's moving up. And now we want to quantify and make a connection to Washburn's equation, which describes actually the process of capillary rise. And if we extract here a time y time slice, we can see that there is the front is going up like this. And to get this front position, we can do a very simple segmentation. I think I have been using just Otsu to do this segmentation, and it worked pretty fine. Next step is to locate the front edge and get the position for each time point. And this will, of course, then be plotted and fitted. And Washburn's equation says, in principle, that the position of the capillary rise is related to the square root of time, which we can very nicely fit in this with a line here. So this is already a full experiment that is done by people working in porous media to characterize their samples before they start doing the full experiment. So this is a very simple example of a dynamic process study. Sometimes the experiments are more complicated, and then you want to tune the experiment before, or at least get some ideas about how to work the experiment. And it is possible sometimes to actually model what you want to see and get some ideas in advance. And sometimes you can't even plan redo the experiment because you inherited the data and you can't redo it. But you can at least use simulation to check a little bit more around boundary conditions. You can also use the simulations for validation of your analysis, and also to determine how many points you need to measure. So there's a lot of things you can actually work with using simulations in advance. So coming back to our old recipes, what we need to do for this analysis, it's essentially the same steps that we have been done many times before. So first step is getting rid of the noise, then looking at the shape of something. In this case, we're talking about the cell image that we have been looking at many times. Then we want to separate cells joined together using the watershed segmentation. And then we from that on, we want to characterize and get distributions of different items in the image. There is a large number of parameters that we need to tune to get this working. So now is a question how to get something more meaningful out with it. Here I start with a very basic simulation. It's actually just a number of circles in a plane. This is actually boxes that should be moving, and they move something like this. So it's a very simple movement going backward, upward in the plane. So let's call these cells that are moving, but usually cells are not moving in a so strict linear fashion. But anyway, now we want to get all the analysis. So what we are doing is first thresholding, which we are doing on this line here. And next one would be to do component labeling, which we actually also do in the same line. So here we do labeling and thresholding in a single execution. Next, we want to compute some properties about the image, and measuring centroids and area from this. And all this will then be put into a data frame, where we can see here that we have label 1 has some position, and area 1 was just a single image, single pixel, and this was in frame 0. So we could actually look at some other frames too, and we can see that X and Y will be moving. Oops, that wasn't meant to. And then we can look at different positions in all the frames. Now we have the positions, and we can tell which frame they are. We haven't really yet told which one belongs to what, and we cannot really tell yet how they are measured, how they are moving. But you can see here that this is from frame 1, frame 2, 3, 4, and 5. And same here, so we can see they are parallel moving. So the motion in this case is a very simple vector, -1, -1. And this, we now want to get some way of measuring how they belong to each other. And we need to match each dot with something else, with a dot in the next plane. And the very simple method to do this is to start with, usually take the easiest first, would be to take the nearest neighbor. So looking in between two frames and see which is the nearest. So don't start with a big gun and try with some kind of extreme multi-hypothesis neural network model. It's probably too complicated. So look first for the easier models and see if they work. And then if that's not sufficient, then you have to go on to the next, more complicated. So tracking using the nearest neighbor is a principle. You have an optimization where we want to find a point in frame 1, which corresponds to a point in frame 0. So we go looking through all the points from frame 1 and compare the distance, the absolute distance between them, between the point in frame 0 with all the points in the other one. And the one that gives us the smallest distance is the one that we say is actually the same point in the next frame. So what we can look at are the distances between the objects. And here you can see there are some long distances and there are shorter distances. And here you can see also the opacity is controlled by the distance. So these are less opaque than those short ones. In this case, it's unfortunately that we have the same distance to 2 points. normally in reality, it's not the case. And what this algorithm does is, if you look at the Python code for it, is actually just taking the first hit as the most relevant one. And it works actually out good. You can see here is a table that was extracted from this. You can see here, and it's square root of 2 and yeah, something, probably square root of whatever, 10 must be, yeah. And then you can see here are some different distances. And now we can see how we can check between. We check each point going through and check and check and check and see which has the shortest distance. And when you do this kind of matching, it's also important that you have a one-to-one relation. So it's not possible that 1 point goes to 2. So you have to really sort that out to make sure that you're not all of a sudden have a split. At least not in this case. There can be processes that where actually the items are really merging and splitting. And that's a more tricky case to track, of course. So the nearest points found were actually the one going -1, -1. So we are good here. And next one would be to track the step by step. So the first one was 0 to 1. The next one is 1 to 2 and 2 to 3 and so on. And we can see here that this algorithm is actually doing pretty well in tracking these points. What you can also do, no, I'm coming to that later, actually. This brings me actually to time for break. It's 10 o'clock, so let's do a 10 minutes. I feel I need to rest my voice a little bit, and then we come back 10 past 10. So see you in short.